Problem number 7. Which? 8. Confirm. Confirm. Opponent challenge the reporter for problem number 8. Another magnetic levitation. Reject. Reporter reject the problem number 8. Problem number 10. Magnetic field. Reject.
剩5题咯。
Number 8.
Reject。
可以吗 ？OK。TA non-spy。
现在开始解进那个第7题。
他在 reject。
不是5题的时候。哦，那我看一下。
在4题的时候。
TA 看一下。TA 确认一下。
还有5题。
哦，没事没事，8分钟你看。
还可以 ，OK。
对，还可以。
Continue 确认一下。Problem number 13. Charge meter. Reject. Reject problem number 13. 这样 TA 可以吗？再来。
可以。
OK。可以好。
可以。
Opponent challenge another
你要付我
problem.
1题啊！你要付我1题。
他说少于5题耶。
等一下。
已经少于5题啦。
现在不是还有5题吗？哦，4题好。
所以要开放哪一题？
所以现在开放，等一下，刚刚是 charge meter， 然后 reporter reject。所以现在剩2、5、7、14、15啊，这些还有5题啊。
是，
这还没有少于5题啊。
7是
解禁了。
哦，所以7大7题解禁了。
7是他刚写上去的。
好 ，confirm。Problem number 7. Joint sounding plate. Accept. Reporter accepts the challenge for problem number 7. Joint sounding plate. Preparation of the reporter 5 minutes. So each team write down your representative name on the blackboard, please.
他为什么也看得到7？你也看得到那个？
上面。
上面有啊。宝宝也拿起来看。那上面就有啊。你为什么也有看到？因为我在等。
第7题。 So now the presentation of the reporter schedule. So finish.
Okay, honorable juries and fellow competitors, I'm a reporter Mike from the Jingchen High School Alpha's team, and we're going to present you problem number 7, giant sounding plate, where we can see the problem statement. It requires us to get the loud and unusual howling sound under the bending of a flexible plate and investigate this phenomenon. So we focus on 2 things. The first is how different ways of bending leads to different acoustic results, and how different physical properties and geometry variation can lead to different acoustic results. And there will be our content. First, we can see from our observation video, where when a very simple phenomenon that a plastic is bent, that a howling sound is produced and it's mixed by various frequencies. And we can see from a slow motion that it's oscillating on this axis, horizontal axis, and this bending provides a force that is perpendicular to the plate, which causes to this vibration. And when we do the Fourier transformation, then we can get the loud and unusual howling sound, which is the problem statement requires. And we define it as the one with the biggest intensity, which we are going to do for the investigation for the following presentation. So next we can see for our theoretical model. From a thesis that we have investigated on internet, that it provides us a view of classical plate theory, where the differential equation of motion can be derived as this, and from this we can get a flexural rigidity derivation. And for this for this thesis, we can also discuss for boundary conditions of the plates. And for the plates, that we use the boundary conditions as 2 fixed sides and 2 free sides, which is described in the paper, and where the paper provides a Rayleigh method that is used to define the deflection function. And the paper also tells us there are different vibration modes that we can do more investigation, but I think that's not our point today. So we'll be focusing on the derivation of our sound, which is the frequency today. So from the deflection function, we can use this function and get the vibration, which the frequency formula is derived from this boundary condition, and we can get the simplified equation from this. And this is how we are going to do for our future experimentation. So let's redefine the problem statement again. After having the theoretical model, we can define the problem statement and really shorten it as a flexible plate is bent, and then as therefore a loud and unusual howling sound is produced. So we need to investigate the bending, where we define the bending as 2 stages. For a static stage, we can investigate the curvature and also the geometry variations. And for the dynamic part, we can investigate the instantaneous force and also the material variations. And for the sound, we see it as the frequency, and we can use fast Fourier transformation to get the required frequency. And for our experimentation, first we can see the static part of our experiment, where we get a microphone here, and we have a steel support and our plate, and also a violin bow in the middle of the plate to provide the force to it, and it can produce the sound. And we also use the finite element method to prove that the static setup is applicable, because it will provide a symmetric deformation when a force is applied on the middle. And for the experimental procedures, first we'll give the plates an initial curvature, and we can use the violin bow to give the center of the plates a constant force. So we can record the sound via the microphone, and we can use the audio data to do the finite fast Fourier transformation for frequency. So here is our first experiment, where we change our curvature, and the dependent variable will be the frequency produced. And for C2 back to our theoretical model, that's when the curvature increases, that the local density, which the curvature is, it will be increased. And so which from the model that the frequency should be decreasing. And we can see from our graph where the curvature square value will have a negative relationship to frequency, and those parameters are shown there. And the second is the thickness of the plates. So about the thickness of the plates, that from the model we have derived that the thickness cube will have a positive relationship with the frequency square value. And for the fitting curve, we have examined that there is surely this relationship between them. And for the width of the plates, that we investigated, and for the theoretical model, there will be the width square value will have a negative relationship to the frequency, and we can also examine by the fitting curve. And for our dynamically experiment, where we use another setup, there is an aluminum frame and a plate that is set up here, and also steel support, and there is a force gauge underneath it and a wood stick to release the setup. So when the setup is released, that there will be a force given onto the plates applied to the Newton's third law of motion. And first we set up a releasing device at a certain height, and we can release the device where we can give a uniform force that is uniform in every experiment. And the device will confront a free fall, which we can get the sound via the microphone, where that's the strip where the plates produces. And we can run the audacity and do the fast Fourier transformation for the frequency. And for the first variable that we do is the material of the plates. And for the material properties, there will be 2 properties impacting this phenomenon, where it's the Poisson's ratio and also Young's modulus. And we cannot find the exact relationship, but we can still observe the relationship between 4 different materials, where it's steel and nickel and aluminum and plastic is used in our experiments. So next one will be the thickness of the plate, where we give the constant force, same force on it, and it will provide a positive relationship with the frequency, where it's examining to the theoretical model. The thickness Q value will have a positive relationship with the frequency, and we can also examine it from our fitting curve. And therefore, we can come to our conclusion. So there will be some possible deviations, because our setup, though we have checked to make it very tightened, but the reporter thinks there might be a little gap, or the vibration will lead onto the setup, and which will cause some acoustic deviation, and that's possible can explain why there is some deviations in our experimental results. And that's for the conclusion. Let's look back to the problem statement again. For the problem statement, it requires us to have the bending of the plates, that we discuss it from static parts and also the dynamic parts to discuss this phenomenon. And where the sound and unusual hawing sound will be produced, that we can acquire it from the fast Fourier transformation, and which we can get the frequency, which is with the most intensity. And for the explanation of the phenomenon, that we apply the Bing theory, which is research online, and which we can get a simple frequency equation that is used to examine our experimentation. And for the conclusion, we see that we use the Bing model theory, and it can be applied from that. We do the fitting of the different powers of frequencies, and it is matched to our theoretical model quantitatively. And the static and dynamic setups are examined to be can be used because of the finite element method that we run on the simulation. And also the deviation is also discussed. So for the final conclusion, that when the curvature square will have a negative relationship to frequency, and the thickness Q value will have a positive relationship with the frequency. And also the width square value will have a negative relationship to the frequency, and then the material properties will also affect the frequency produced because of its Poisson ratio, and also the Young's modulus of elasticity. And the relationship is still unsure, but it can be do more in the future investigation. So the next one will be the thickness Q value will have a positive relationship with the frequency under the dynamic experiment. And I think that's all of our presentation. Thanks for your kind attention.
Thank you very much for your presentation. Now the opponent asks the questions to the reporters. 2 minutes.
Judges and fellow competitors. So first question I want to ask is, on page 33, you mentioned that.
Pardon, which page?
33.
33.
You mentioned that the Bing theory.
Yeah.
Yeah. Is your plate thin enough to use the Bing theory?
So that's the thing, that we don't think that the Bing theory can be totally applied to our model, but it can still be used to see the plate's vibration, because the geometry is kind of the same. So we only have the quantitative explanation to the theory.
Okay, thank you. And the next question is, you said that you use the dynamic setup, that you drop the weight down and cause the vibrations.
Yes.
And does it produce other sounds like the dropping sound or something else?
Yes. So there is still some noise, but the noise can be cancelled through our audio software, which we can cancel to the noise from the recorded, and we can cancel it to the wave of the experiments that we have recorded.
Okay, how do you cancel it? Is it the software do it, or you record the noise background, or
Yeah, so we recorded noise background and we put it into a software to do a noise reduction.
Next, you said the same the dynamic setup. The plate is still bending.
Thank you. Now we move to the preparation of the opponent. 3 minutes. TA. Now the opponent, Ian, takes the floor, making about 4 minutes. Honorable judges and fellow competitors, we're from Team Trivial. And the question is number 7, giant sounding plate. So the problem. So in the first. So this is the problem statement. And these are the key points within the key points is the frequency and mechanism. And the reporter reports that their theory is plate theory and a beam theory. And they use Valley fault to provide the constant force of the plate. And then
drop the plate to bend the plate, and then they investigate the thickness, the width, and the modulus parameters, and then discuss the deviation of the plate. Here are the advantages. So first, the report is loud and clear, and the theory is clearly explained, and then different parameters are discussed, and discussion of the deviation of the plate. Here's our suggestion. You can consider the deformation of the plate and the definition of the howling sound. Right, so the points to discuss is first the definition of the howling sound and main theory limits and the shape of the plate. Alright, so I would like to invite the board.
Go to the discussion.
Alright, so first, what do you think the definition of the howling sound is?
Just as our problem statement definition produced, that we define it as a sound that we can record it from the fast Fourier transformation. We can get the highest intensity, and this is this so-called loud and unusual howling sound that we use in our investigation.
So if you bend the plate, there's going to be lots of modes of vibration.
Yes.
And how do you make sure this is the right one you want to choose? Or is there a more lower or higher?
Oh yeah, sure. There will surely be some lower or higher modes but under the certain conditions that the sound that is produced must be under the fundamental mode of the fundamental frequency that is under the same material or geometry conditions, and that the fundamental frequency is produced. So we only observe for the highest intensities fundamental frequency.
Okay. Next one here. So the shape one. So you said Anthony, turn the page to the static setup.
Yes. So this is the static setup.
So let's see, you press the plate over here and
Yep.
give a force using a violin bow.
Yes.
And just the force on the violin bow cause the plate to bend more or bend less, or does it matter?
Yeah. At this part, the reporter agrees partly with the opponent that the violin bow will truly make some of the bending to the plates according to some mechanics theory, but there is still, we try to reduce our deviation, and from the recording audios that the effect of this is not that much because we can still get the highest intensity of the acoustic sound. But there, the deviation should be discussed as the reporter agrees with the opponent.
Okay, so the next one is the dynamic setup.
Here is the dynamic setup.
Thank you. The dynamic setup, you put a weight to bend the plate, and
Yes.
in our experiment, when the plate bend more, the frequency will increase. So if you do the fast forward transform, do you do the whole sound to analyze the frequency, or you slice it into different parts and analyze it?
Yes, of course we do the whole sound because when the stroke happens, that the setup will undergo a instantaneous sound happening, and we have the sound that is analyzed, And yeah, there should be more sounds produced, as the opponent said.
Okay, so the next question is, the dynamic setup will move the plate, and what about the microphone? Is there the distance change will it affect the sound recorded?
Oh yeah, so if the distance, of course we installed a microphone on this setup, but it's not visible here. But surely if the microphone is, we agree with the opponent that if the microphone is installed in other places, that there could be, the intensity could be different, and the difference is that what we can discuss for, and so at this point, that other sounds, other frequency may be the main point of the fast Fourier transformation. So yeah, we should avoid this deviation, and we did avoid the deviation from setting microphone over on this setup from jumping parts, and at this part the opponent provides a good view of the deviations.
Can you turn the page to the one with experience with the wave part?
Pardon?
Can you turn the page to the experiment with the wave?
With the width?
The
Oh,
wave.
width. Okay, so it is here. Right.
So how do you define this width here?
Oh yeah, of course the width is just like the boundary conditions provided in our theoretical model. The width is defined by the beat here, which is restricted, and that's how we define our width.
Okay, so what about the length?
Length. Oh yeah, we control the length of every plate, and we didn't do the discussion of it.
But in our experiment, the length affects the most, affects more than the width.
So that the reporter would like to ask the opponent to, maybe we can discuss what you think will affect from the length. Yeah.
Wait. And it's two ends here. And then everything just rest will be like
Stress.
this direction.
Oh, yes.
Yeah, and the stress causes the vibration. So if we increase the length, the wave distance of the wave will increase too, because it's due to
The way it should increase.
the wave, but the width part, these two photons, the side is mixed. So I think there's no vibration. This.
Okay, so here the opponent provides a view for us that when the length of the plates increases, the wavelength will also increase. And at this part, the reporter totally agrees with the opponent. And for our equation, we can also see that the frequency is also affected by the length of the plates. And at this part, I think the opponent provides a good discussion, and maybe there is other points that we want to discuss. Please continue.
setup
Yes.
to measure the force given to the plate?
Yes, from because we have released it from a certain height under every experiment, that we think from the Newton's third law of motion that the given force will be given by the dropping force, which is the gravitational force. And from setting at a certain height, it can be controlled and fixed. Or maybe a reporter would like to invite the opponent to discuss the point that you have raised. What will happen if there is this directional vibration?
This side should be replaced because prevent the vibration to reduce. So if this point fixed like this, then it might produce a vibration in this side. But in the experiment that we presented, these two sides are fixed.
Yeah. So here, opponent provides us a new view of experimentation where we can release this side and give us a free vibration, and we can get another kind of vibration motion, and we can do the discussion of it. And this part is maybe we can do in the future work, and maybe we can see what you said that when the length increases and we fix these two sides, you have mentioned that this place will have vibration, right? So if I think it's because of the Poisson ratio, then there will be deformation on this side, which causes to some acoustic effect. You agree with it? Okay, so and this class, maybe it's a more deviation that we can discuss in the future work.
Right.
And thanks for the opponent.
Summarize the discussion, 1 minute.
So in the discussion, before the court mentioned that the definition of the howling sound is the sound that they get, the highest, the loudest sound that they, loudest frequency that they get, providing force to the plate. And then the experiment set up in violence ball, it surely slightly deviates the board, and in a dynamic setup, it surely change the distance between the board and the microphone. And in the data analysis,
Thank you. So now the reviewer asks the questions to the reporter and opponent 3 minutes.
Okay. So my first question is for the reporter. Do you control how much the ball, like how much the force the ball acts to?
No, there will be deviation, but as we can see, the frequency won't be impacted by the force that we given it. It's only the intensity.
Also, their point is just to give a force and. Okay, so I want to ask, do you agree with the reporter about this part? So, okay. The second question, so the opponent says that he does not agree that the beam theory can be used in this situation. Okay. Can you please explain why do you think that it's not appropriate?
It's a limit of the beam theory that if the beam is not thin enough, then they produce a little there's an error in the calculation.
Okay, so
It's the natural limits of the theory.
okay, I see. And then okay, and again for you, I want to know. So you mentioned about the background noise, right?
Yeah.
Okay, and so okay, and so for the recorder, how did you cancel the background noise?
Yes, as we have discussed that you input the noise audio into the reduction side and it can cancel out from the software.
Do you think the background noise is a big, like, is it significant? Like, will it provide a significant
At this point,
glitches?
recorder doesn't think so, and because the intensity is not big enough, and also the frequency is very low at this point, so that's the noise frequency is very low, and we can easily separate it from the real frequency that we are going to find.
Oh yeah, so because the frequency that you want to find is higher
Yes.
and will not be
Yes.
affected by
And
the
the
lower.
intensity is very high.
Okay. Yeah, I think that's all. Thank you.
Thank you. So the preparation of the reviewer, 2 minutes. Now the reviewer takes the floor. 4 minutes.
So I'm the reviewer from Leading Senior High School, and this is the question. So John Xiaoming. Okay. So first, this is the summarize of the reporter. They use the violin ball and also the beam theory and find out the relationship between different parameters and frequencies. So first, for the reporter, their strengths. I think their presentation is really fluid, and they clearly explain the theory and the experimental setup. And the experimental setup was really nice. But for the areas of improvement, I think the data is not enough, and it's lack of quantitative link between theory and data. For the opponent's difference is that they mentioned a lot about the myths of the recorder, including like the background noises or the and also the beam theory. But for the areas of improvement, I think the sound of the opponents isn't validated. And then here's the discussion. First, about the background noise. The opponent asks how to cancel the background noise. And for the reporter, he says that he recorded the background noise and used software to cancel it. And in this part, I agree with the reporter. I think it's a good way. Okay. For the beam theory, the opponent says that it can only be used on thin sheets. For the reporter, he agreed with the opponent and said, yeah, the beam theory cannot be totally, so he cannot totally apply the data to the theory. In this part, I agree with the opponent, and yeah, because there are some limits of the theory. For the definition of holding, the opponent says said that the reporter did not define the holding, and for the reporter's responses is that he defined the holding by the frequency which has the highest intensity. And then for the influence of frequency, the opponent thinks that the frequency is influenced by the length of the plates, and the reporter agreed with that and said we'll consider more in the future. For this part, we agree with the opponent. And yeah, I think that's all. Thank you.
Thank you. Now the concluding remarks of the reporters. 2 minutes.
Okay. So in the concluding remarks, that in the opposition part, we have discussed various boundary conditions such as the lengths and different vibration models, and they are discussed, and that is what the reporter thinks we can do in the future work. And also we discussed some deviations like the noise reduction and something, and also the opponents said that the beam theory is not applicable, and yeah, we surely only do the qualitative explanation, and that is what we can do for a precise quantitative experimentation by doing experiments to vary our theories, to examine our theories for a theory that is really can use to do a quantitative experimentation. And for the reviewers' parts, they give us a point about to do the quantitative experiment to a theoretical model. And yes, so in this part, we can maybe apply more like empirical equations that's from our experimental data, and we can also use it to quantitate my experiments. And there are still some efforts that we can do to reduce the noise that we agree on it, and that is all of my concluding remarks, and thanks for your kind attention.
Thank you. The questions of the jury, reporter, opponents, reviewer, stand up. Questions?
Can you go? So I have a question for. So my question is like, can you go to the page itself? Because I saw there is a reference. So my question would be like, is your theory from this reference or?
Yes. Yes. The model is from.
Okay, so basically, your experiments would like to somehow verify
the model, because the model is too complicated. It's discuss different vibration modes.
Questions from the jury? Professor Nian?
So, what kind of boundary conditions? How does the boundary condition would affect the major peak of the sound frequency?
Oh yeah, so we use this kind of boundary condition where we restrict two sides, and there will be more boundary conditions as the thesis have showed us, and such as this kind of boundary conditions, there are like 5 vibrational models, and if we clamp this side or we clamp this side, there will be more vibration models, like the vibration will happen in the middle, and that is more interesting to discuss, but is complicated to make the model.
Any other questions? I have a general question for each team. General questions. What the key parameters for producing the joint sum plate? What the key parameter do you think for producing the joint sum plate? Anyone want to answer the question first?
So the key parameter will be, if it's talking about the frequency, it will be the curvature, and if it's talking about the phenomenon, it will be the force that applied on it, which the strength changes, and it gives a perpendicular force to this plate.
So you think it's a bending force? Is
Yes.
a key parameter for
To the
producing
curve phenomenon.
joint sounding plate.
Yes.
Opponent, reviewer want to answer these general questions? Opponent,
The opponent agrees with the reporter.
so you agree with the reporter point? It's also bending force played a key role for generating, producing the joint sound plate. How about the reviewer?
I agree with the reporter also, and I think that some like the different materials will also impact the results.
Material problem. Any questions? Professor Gu.
So my question would be like on the high school students level, if I was a high school student, I can imagine that the sound should be somehow like produced by the wave effect on the plate. This can sound like it's like a spring, and if you have some force, so this force would be something like, as you mentioned, it's bending force. So and the fall, so therefore you like a string, and there's you put some force on this string, such that you becomes a wave, and due to some materials property, they will be vibrated together, such that it will make some noise. So my question would be like, why this kind of concept is not correct? I mean, you don't consider this kind of, you don't consider in this kind of direction.
May I ask, are you discussing about the deviations from the material properties?
No, I'm just thinking that for me, it's look like just the wave, the result wave.
Also,
Yeah, Professor Gu mentioned for the single pictures to generate the wave, just apply the external force
Professor, thanks.
and generate the acoustic wave.
Yes.
What do you think about this simple idea to apply this problems?
I got an idea to do the experiments that we can put some diazotic plates that you can detect the change by outputting voltage, and we can observe the wave form of it from getting the voltage outputs. But because in this problem the wave model is too much and too complicated, we don't know which one it actually is. So we only discuss about the frequency that is the problem statement task, and it's a good point to do the future experiments.
Thank you. Any opinions from opponent and the reviewer? When you learn the simple picture from your high school textbook, how do you use that picture to consider this problem? Could you give us some of your opinion, opponent, reviewer? Okay, reviewer one.
For our opinion, we don't think the one-dimension vibration is correct. Like, we should consider two dimensions.
for this case, coordination or vibration. Opponent, do you have any idea?
I think we could just focus on one dimension plus the two side of plates and or just bent it in the middle. And the other side, it will introduce a standing wave inside the plate. So this is another investigate.
Thank you very much for the briefing. So please sit down and waiting for the jury.